Hi guys, welcome to my channel. Today we are going to study about segment tree, a data structure which is useful in answering range queries. So let's study about segment tree. So segment tree stores information about array intervals as a tree. This allows answering range queries over an array efficiently. How efficiently? Each query can take up to O of log n time, which is faster than if we do it in brute force. So, two examples of what can be done with segment tree is that if we are given a question that find sum of consecutive elements in the range of L to R and also find a minimum element in the range of uh, L to R, then we can do it in segment tree efficiently. Uh, Also, if we consider uh, this question, sum of consecutive elements, you will be thinking that we can do this in O of 1 by using prefix array, right? But if what if I tell you that if I also want a functionality that I can be able to update one of the index and still without rebuilding the prefix array, I can get the answer, then uh, for segment tree in this case would be much more efficient because update queries also in segment tree takes log n time, and also the after that if you want to find the sum of the range, then it will also take log of n, so which is much faster than the prefix sum approach. So now properties of segment tree. Uh, these are the two properties which are most famous. The first one is that segment tree uh, can be easily generalized in multiple dimensions. Right now, we are only talking about a 1D array. If suppose I am building a segment tree on top of my 2D array or 3D array and or so on, like n dimensional array, then my complexity of segment tree will not vary that much. It will only vary in power of dimensions. What I mean by that is, suppose that for two-dimensional segment tree for a matrix, the time complexity would be log n square, and suppose like for three-dimensional array, it would take log cube n, big of log cube n. So that is how segment tree can easily be generalized. Second one is standard segment tree requires 4n vertex for working on array of size n. So when we will be building our segment tree in the form of binary tree, then for a array of size n, the most uh, vertex that will be required is 4 of 4n. So I can give you a proof of that as well. Suppose that I'm building a segment tree, a binary tree. Suppose then I'll be having what I'll be having log n levels. So and so on over here. Now, let's count the number of vertex. So our root will have 1, second level will have 2, then 4, and so on. Till what? 2 to the power log n, right? So this will be our number of uh, number of nodes that we'll be having, the number of vertex that will be having in segment tree, which is less than 2 of log n plus 1. And this 2 log n plus 1 is less than 4n. So that is how I can say that standard segment tree requires 4n vertex for working on array of size n. Alright. Now let's consider an example. Uh, Given an array of size n, we need to do two types of queries. First one is compute sum of elements between range L to R, and second one is handle changes if the value at index I of array changes to x. Also, for both the queries, the time complexity should be big of log n, right? For this, if we want to come up with a solution, so first let us think about the brute force method. So for our update query, it will take O of 1 constant time. We will just change array of I to x, and now if we want to compute the sum, then what we'll do, we will traverse from L to R, and we will take the sum of the elements. The second approach, which is little bit efficient on the sum side, is we take prefix sum. So what I mean by prefix sum is, suppose that my array is 1, 2, 3, 4. Then what I do is, I take a prefix sum. I make this array into a prefix sum array, and by that what I mean is the first element will remain 1, then the second element will be this plus the previous sum. All right, like the previous prefix sum element. So this will be 3, so that means till here the sum is 3. All right, then till from here to here it would be 3 plus 3, that is 6. And if I want the fourth element, that would be 4 plus 6, that is 10. So that is how we compute the prefix array. So it will just take us O of n time to compute this prefix array. And if we want, suppose to take a sum of a range, then what we'll do, suppose that I want to know the sum of this array, right? So what I will do, I will just do 6 minus 1, all right, that is 5. So, and here we can see, uh, 2 plus 3 is 5. So that is how we take sum of a range using prefix array. So the formula is something like, suppose we want to take from L to R, right? So it would be array of R minus array of L minus 1. So using this, we can do some query in O of n. But here also there is a problem. Like if we want to do update element, then we have to update something over here. And if we do this, we need to recompute our prefix array. So if we take prefix sum, it would take O of n time. Now let us study about the third approach, which is the most optimal one, and which is using segment tree, in which both of the queries will be able to do with time complexity log n, right? So let us consider an array of 4 elements. This array has elements 1, 2, 3, 4, uh, and the index would be 0, 1, 2, 3. So first step in solving a question using segment tree is, first we have to build segment tree. For building segment tree, we need to know about two things. First one is that each node represents a range, and the second one is how we represent the nodes in terms of an array, what the index of each node is. So if we suppose root of the segment tree, which is the root node, uh, is having index 1, then the left node will have index 2 into, sorry, if we suppose that root of the index is I, then the left node will have index of 2 into I, and the right node will have index of 2 into I plus 1. All right. So taking care of these 2 points, now we will construct our segment tree. So I'm going to show you how I'm going to construct segment tree for this. First, uh, I will take a I will take a root, and root will represent elements from 0 to 3. So 0 to 3. Now the left will represent half of this node's range, so which is from 0 to 1 index, and the right will have the other half, which is 2 to 3. And similarly for this node, till we reach the very leaf where we will have only one index, then we will have this 0 0, and here 1 1, and this will be 2 2, and this will be 3 3. Once we have reached over here, and see this also, the first point, we have represented each node in terms of index, and the second point is that the index of this node is 1, then this index of this node is 1 into 2, and this node is 3, which is 1 into 2 plus 1. And similarly, this is 4, this is 5, this is 6, this is 7. So which means 2 into 2, which is 4, and 4 plus 1, 5. So this is also satisfying, right? This condition also. So now how we are going to know the value of each node? For that, once we have reached the root node, what we'll do is we can build this using recursion, which I'm going to show you the code of which I'm going to show you in the next video. Just now, right now, just bear with me and just get the idea of how a segment tree is visualized. So the root node will have value of what? It will have value of 1, this one, because it is representing sum from 0 to 0 index. And similarly, the value of 2 here value of 3 here, value of 4 here. And then what we do is we back propagate. So we back propagate. So when we back propagate, the value, similarly here we'll back propagate. So the value would be the sum which we got from the left and the right. So which is going to be 3, and here it is going to be 7. And similarly, we will, when we back propagate from here, then we will have value of 10. All right. So from 0 to 3, our sum is 10. From 0 to 1, our sum is 3. From 2 to 3, our sum is 7. And from 0 to 0, it's 1. 1, 1, it's 2. And now the second thing comes. Now our first step is done, which is building of segment tree. And now the second part comes where we will be answering our queries. So how we are going to answer it is, so let me first write it. So sum query. All right. Let me just copy this tree. Okay, so I have copied this tree over here. Now if I want to know what is the sum from index 0 to 1, it is easy, right? What I have to do, suppose that, let me write it. I'm going to answer three queries. First is what is the sum of from 0 to 1. Second one is what is the sum of, actually two. Basically it will only take two queries to understand how the sum query works. So second one is from 1 to 3, and that's it. So how I'm going to solve the first one is, uh, I'll start from here. So this node represents 0 to 3. All right, so I won't get the answer from this value. So what I'll do, I'll check that which direction does my this query lies. So it lies on the left side. Then I will go to the left side and check if the node represents this range. Yes. So now this node represents from query from 0 to 1. So the answer of this query is 3. So this is how we have solved the first one. Now for the second one, which is quite tricky because know this, we want the value from 1 to 3. And now if we stand on the root and we want to figure out which direction to go, then we will be having one confusion that uh, on the left side we will have partial question which is 1 to 1, and on the right side we will have the other partial question which is 2 to 3, and the sum of which represents 1 to 3, right? So that is what we are going to do. We are going to do both the calls, and we will be having we will be calling it using a query of 1 to 1, and here we are going to call it using query 2 to 3. So from this side we will get an answer of 1 to 1, and from this side I am going to have answer of query from 2 to 3. So I will have answer of 1 to 3. So how I'm going to do it is like this. First I'm going to send it the query 1 to 1. So this will look at it and it will send 1 to 1 query to here, and I will get 2 from here this side, and this side I'm going to send query 2 to 3, and from here I'm going to get 7. So 2 plus 7, which is 9. So 9 is our answer of query 1 to 3. All right, that is how I'm going to solve the question for sum query. Now that I am done with my sum query, let me show you how update query works. In update query, what we are doing is we are updating an index I with value x. Let me take an example. Suppose I want to update the first index as 3. Now, what I will do is, as I know that I want to update the index of uh, uh, value at index 1. So what I will do is I will propagate till index 1 in my segment tree and update this value to 3. Now when I back propagate over here using my second property of building, which I had, that if the index of this node is I, then this node is 2 into I, and this node is 2 into I plus 1, then what I will do is segment tree of I is equal to segment tree of 2 into I plus segment of 2 into I plus 1. And this is how I'm going to update this index. So this index will become 1 plus 3, which is 4. And over here as well, I'm going to use this formula and I will get 4 plus 7, which is 11. So that is how I'm going to update my segment tree. So this is how we do update query. So that's it, guys. In this video, we have just gone through the theoretical part of segment tree, and we have visualized by looking at one example of update query and sum query, that how we are going to uh, visualize our segment tree. In the next video, I'll show you the code of this exact example in C++ and how we are going to code build function, update function, and also sum function. That's it, guys. If you like my video, please do subscribe to my channel, and also please like this video and share it with your friends. Thank you.